This is ligand substitution reaction. Always remember the stronger ligand is going to substitute the weaker ligand. Okay, more reactive ligand is going to substitute the less reactive ligand. Always remember. So if you can see this, this is copper 2 plus. Okay, and once you are going to uh, add copper 2 plus in a solution, so you will see that the water would be surrounding this copper 2 plus. So it would be forming this CuH2O6, and this is the charge of copper. There is no charge on water. That's the reason you are going to have this charge. So this is of copper basically. And then then I'm saying that you are going to add NaOH into this solution of copper 2 plus. Then what would you observe? So first of all, when we are going to add sodium hydroxide, basically we are going to add OH minus. Okay, this is a base. It's going to provide OH minus. This is a base. It's going to provide OH minus. Remember. So this is water. This is water. So OH minus is going to take its proton. Okay, OH minus is going to take its proton just like that, and would be leaving behind OH and then OH. So how many OH you have right now? Two OH. So you can see this, two OH, and then H2O4. 1, 2, 3, 4. Because we have added few drops of sodium hydroxide. That's why. Okay. So what's the charge on this complex? You will say 0. Why? Because copper is +2 and OH is -1 and -1. So -2 and +2 overall is 0. That's why there is no charge. Whenever you can see there is no charge on any complex, so you can say that this would be PPT, not an aqueous solution. This is the hint for you. Okay. Whenever you can see no charge on any complex, that is 0. So you can say that this is PPT. Then the color would be depending upon the metal. So this is blue PPT because this is copper. Shorthand representation, you can represent it just like that. Okay. So this is the product when you have added few drops of sodium hydroxide. Then I'm going to add excess. You can say sodium hydroxide. Okay. So PPT dissolves to give deep blue solution. PPT dissolves to give deep blue solution. Remember. Okay. And then ammonia to copper solution. Like I'm going to add ammonia in this, then what would you observe? So when ammonia is going to react with water, it's going to give you ammonium and OH minus. Of course, OH minus is a ligand. So same goes with this. I'm going to add OH minus, and it would be giving you this product. This is blue PPT. This is blue PPT. Okay. Also you can represent it as copper +2 reacts with 2 OH minus ions, which is coming from ammonia. It would be giving you copper hydroxide, that is CuOH2 solid. So CuOH2 solid is blue precipitates, blue PPT. Okay. Then I'm adding excess ammonia. Excess ammonia. So, here we have 2 OH, and right now we have 4 OH. So you have added aqueous ammonia. So that's the reason more OH negative ions you have. So they would be taking more protons from water, and it would be giving you deep blue solution. That's it. And important thing is that coordination number is not going to change. Coordination number is 6 and coordination number is 6. You have to take care it off. You would be mentioning that like smaller things. Okay. Only the change in color is observed, not the coordination number. Remember. Or you can see the charge. You can see the charge. There is no charge on this complex. There is no charge on this complex. But if you can see this complex, if you can see this complex, so it's copper plus 2 and it's OH minus. 4 OH minus means minus 4 means minus. So plus 2 and minus 4 would be minus 2. Would be minus 2. Okay. This is a summarized reaction. Let's suppose you have copper complex, adding few drops of ammonia, you would be getting this. Adding few drops of sodium hydroxide, you would be getting this. Then adding excess ammonia, you would be getting this. Then adding excess ammonia, you would be getting this. Okay, this is of copper. Then we are going to discuss how would, like, what we would observe when I'm going to add HCl to this copper 2 plus. Cl minus is acting as a ligand, so I would be observing this. You can see the coordination number is totally changed. Coordination number is totally changed. Okay, concentrated HCl. Okay, so we would observe yellow solution. It's not yellow ppt, it's a solution. Why? Because there is a charge. Why? Because there is a charge. Okay, so you have to memorize these all things. Okay, even you have to memorize the color. This is very important in Edexcel. Okay, and then we are going to discuss the chemistry for let's suppose, first of all, let's discuss the chemistry of nickel nickel 2 plus. Okay, generally the charge on nickel is plus 2. Okay, so nickel 2 plus. So when nickel is going to react with water, it's going to form this complex, just like copper, just like copper. And this is green, and this is green. Okay, now I'm adding ammonia in this solution. Add few drops of ammonia. So same as copper, I would be getting this, and there would be no charge. You know why? Because this is minus 2 and this is plus 2. So of course this is not a solution. It's a gray green precipitate. Okay, then I'm adding excess ammonia. So what we would observe, adding excess ammonia. So okay, because this is a charge of nickel, and this is replaced, substituted by ammonia. All of the things are substituted by ammonia. All of the things are substituted by ammonia. Or, or you can also write, or you can also write nickel, NH3 4 and OH NH2O2. You can also write this. Again, the charge is +2. And remember, this is a blue solution. Second thing that you need to memorize. Okay. Then I'm adding concentrated HCl, same as copper, 100%. Then I would observe nickel chloride. There is a charge that is +2. There is a charge that is +2 is formed. So you know what's the color? You know what's the color? Yellow solution. Yellow solution is observed. Then we have chemistry of cobalt, that is 2 plus. The general charge on cobalt is +2. Okay.
Sir, what's
Cobalt.
the charge on Cl?
Cl is -1.
And
Cl is
nickel
-1.
is +2?
Yes.
Okay.
Cobalt, when it's going to react with water, it's going to form this. 6 and the overall charge is +2. And this is pink. This is pink in color. And then again, I'm going to add sodium hydroxide in it. But few drops. So I would see this. And then this is removed. So there is no charge on this. So I would observe blue precipitate. So I would observe blue precipitate after adding sodium hydroxide. Okay. And then what if I'm going to add ammonia, excess ammonia? What if I am going to add excess ammonia? Add excess ammonia. So cobalt H2O 6, the overall charge is 2 plus 6 ammonia. It would be forming this. Again, the overall charge is 2 plus. Because there is no charge on ammonia and 6 water molecule are displaced. So we would observe, of course, this is not a PPT because there is a charge. So we would observe yellow brown solution. yellow brown solution is observed. And then I'm adding concentrated HCl. So of course there is a charge, so there would be a solution. It's not a PPT. So I would observe blue solution. If you can notice this, in the reactant side we had 6 ligands. In the product side we had 4 ligands, like especially with Cl. Cl4, Cl4, then Cl, then we have copper. We had copper. It was also Cl4. You know, the size of chlorine ligand is more than that of water. So you cannot add more than 4 chlorine around any metal. It's just like that. The size of a chair is longer, is larger. So how can you add more chairs along, like around your dining table? It's not possible. If you have the ligand which is having a smaller size, so you can add multiple chairs. But if you have those chairs which are going to have larger in size, so you cannot add more chairs. Same goes with this. Since the size of a chlorine ligand is higher, so of course you would be adding only 4 chloride, only 4 chlorine. Okay, so this is important to know. Then after that we have zinc 2 plus. We have zinc 2 plus. We have zinc 2 plus. Okay, zinc 2 plus. If you are going to add water, you will see that you will see that it would be forming. And one thing that I'm going to tell you that um, it's not a transition element. We discussed in the first class of transition metal that it's not a transition metal. You know why? Because there is no any unpaired electron in this after getting 2 plus. Any unpaired electron basically. So it's not a transition metal. So you won't see any color. It would be always forming white, 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 white solution, white solid, white solution, white solid. Remember, okay? So if you are going to add zinc 2 plus in, you can say, let me write it down that it's not a transition metal, first of all. So you will see that this is important to know. Okay, or add. Few drops of NaOH. It's a solid. Okay. Then So precipitate dissolves. Precipitate to give solution. So this is the chemistry of zinc. This is the chemistry of zinc. Okay. And then you need to know, and then you need to know um, colors of vanadium. It's in your syllabus. They have mentioned that you need to know different colors of vanadium. Like I mean that if you have iron 2 plus, so you know it's green. If you have iron 3 plus, so it's reddish brown. But if you have vanadium compounds, let me tell you this, colors of vanadium compounds. So you will see that we have sometime V2 plus, we have V3 plus, sometime we have V4 plus, sometime we have V5 plus. You will see that V4 plus is present in this, and V5 plus is present in this. So you know the color of V2 plus is purple and V3 plus is green, V4 plus is blue, and V5 plus is yellow. Okay. And then um, what are the colors? And then what are the colors that form green solutions? Okay. What are the colors that form green solution? Like I mean to say, um, like let's suppose iron 2 plus is green, of course. And you know, it's also green. And you know, it's also green. Not only this, you will see that nickel is also green when it's 2 plus. And not only this, you will see that when chromium is plus 3, so this is also green. This is also green. So the metals are different, but the colors are same. Metals are different, but the colors are same. So remember that um VH2O6 overall charge is plus 3. Overall charge is plus 3. So remember that uh, this and iron H2O6, but 2 plus, nickel H2O6, 2 plus, and chromium H2O6, 3 minus. These are the four complexes. These are the four complexes that is of green solution. Remember. Uh, uh, okay, no problem. ओके जी। अच्छा जी। Okay, then we have chemistry of chromium, you know, then we have chemistry of chromium, then we have chemistry of chromium, like you can say that Cr3 plus. This is the common charge on chromium. When you are going to add water, you would see that chromium H2O6. As you know, there is no charge on water, so the overall charge on complex would be the charge of chromium, that is +2. And this is this is what? What is the charge on this? Chromium H2, oh, chromium H2O2, chromium H2. Sometimes it's +3 and sometimes it's +2. So I'm going to tell you both. I'm going to tell you both. Cr2 plus H2O. It's going to give you CrH2O2 6, and overall charge is +3. So this is blue and this is purple. This is purple, okay? Because the ligand is attached, that is water. Then I am saying I'm going to add sodium hydroxide. I'm going to add sodium hydroxide, okay, into this complex. So remember that uh,
Sir, doesn't chromium also have a +7 oxidation state?
chromium, no. It's manganese. Highest oxidation state on manganese, that is +7.
Oh, okay.
Yep. CrH2O6 3 plus OH minus, and I'm going to heat. I would see that chromate ions would be formed. You know what is chromate? Chromate means CrO4 2 minus. CrO4 2 minus. So, and then moreover, I'm adding again sodium hydroxide, or you can say adding H plus, adding acid. So you will see that this dichromate is formed. Dichromate, that is Cr2O7 2 minus. You know what's the color? You know what's the color of dichromate? Orange. Orange. And what is this? Yellow. Yellow. And if you are going to deprotonate this, you have added H plus, and if you are removing H plus, what do you mean by this removing H plus? You should add OH minus. You should add OH minus. So you will see that it would be coming back into the reactant. It would be coming back into the reactant. Okay. So then we are going to relate entropy and complexes, like complex compounds. What is the relationship between the complex compounds and the entropy of the system? So, we have formed we have prepared a lot of complexes. Some complexes were having monodentate ligands, some complexes were having bidentate ligands, some complexes were having polydentate ligands. Some are stable and some are less stable. Some are more stable and some are less stable. So remember, uh, entropy, entropy and stability of complex and stability of complex. So if your delta S system, because we have two types of entropy, system and surrounding. I'm talking about the system. That's why I'm going to mention it. If the delta S is more positive, if the delta S is more positive, so remember there would be more stable complex ion. This is important. Okay, simple. Uh, so then how can we have the values of entropies? Of course. Hmm? How can we have entropy values? So he would be giving you the values for the entropy of that particular complex. Okay. So we have monodentate ligand, we have, you can say, bidentate ligand, we have hexadentate ligand. So they would be forming, like, as a random question, if I have hexadentate ligand, that was EDTA. Okay, that was EDTA. So it forms more stable complex. It forms more stable complex. So you can say that, and when the examiner would be giving you the value, so it would be more positive. So you can say the complex is more stable. But of course, you can decide after knowing the values for the entropy. After knowing the values of the entropy. Okay. And then we have catalyst. Then we have catalyst. What is catalyst? What is catalyst? Remember, catalyst is a substance which is going to increase the rate of reaction, which is going to increase the rate of reaction and decreases the activation energy and provides alternative pathway. What is catalyst? Number one, number one thing is that it increases rate of reaction, decreases activation energy, provides alternative pathway, without its being used. Without its being used. Okay. So we have two types of catalyst. Number one, we have homogeneous catalyst. Then we have heterogeneous catalyst. Homogeneous catalyst means that when there is a same phase, same state of reactants and catalyst. Let's suppose if your reactant is a gas and catalyst is also a gas, this is homogeneous. If your reactant is solid and the catalyst is solid, this is homogeneous. If your reactants are liquids and your catalyst is liquid, so you can say this is homogeneous. And what if you have heterogeneous catalyst? When different state of reactant and catalyst and catalyst. Okay. So let's suppose, let's suppose um, we can define homogeneous catalyst. First of all, you need to know the graph of homogeneous catalyst. Okay. So you can see that if this is reactant and this is product. Okay, this is product. So I can say that this is activation energy EA. EA. Okay, and then okay, so this is your activation energy, but this activation energy is for without catalyst. That is higher. And this activation energy is with catalyst. This is also activation energy with catalyst. Okay. So you will see that after addition of catalyst, the activation energy would be lower. And why you are going to have two humps? This is the first hump, this is the second hump. Whenever in your chemical reaction, the intermediate is present, so you will see that the graph would be having the two humps. Okay. So what do you mean by intermediate? I was telling you, like, let's suppose if you discussed SN1 reaction that occurs in two steps. In the first step, the ligands are going to leave the compound. Let's suppose you are going to substitute OH minus, like Cl minus through OH minus. This is called ligand substitution reaction, or you can say nucleophilic substitution reaction. So in the first step, the nucleophile would be leaving the substance, and of course the intermediate would be formed, and in the next step the coming nucleophile would be attacking on that substance and would be forming the product. It means that this reaction is going to have two steps, so that's why you can see this curve. You can see this curve. Okay, if you have a reaction in one step, so you will see only this, and if you have two steps, so you can see this. Okay, then uh, I can say that, let's suppose Okay, so we have a reaction like how the homogeneous catalyst works. How the homogeneous catalyst works. So you can see that we have a reaction in which S2O8 2 minus is going to react with 2I minus is going to form 2SO4 2 minus and it would be forming I2. So you can see aqueous, aqueous. Reactants are aqueous. And this is catalyst that is also aqueous. This is homogeneous catalyst. This is homogeneous catalyst. So it's very interesting reaction. You know, after looking at the reaction, I can say that this reaction is not possible. If you're thinking why it's not possible, because how it's possible that the two negative substances are going to react with each other? Aren't they repelling each other? They are repelling each other, but the catalyst is going to work in this. So we would say like how the iron 2 work over there. So first of all, iron 2 plus would be reacting with S2O8 2 minus. It would be forming sulfate ion and iron 3 plus. Iron 3 plus is oxidized and S2O8 minus is reduced. And in the second step, iron 3 plus would be reacting with I minus. It would be forming I2 again iron 2 plus. You can see, you can see if you are going to add these two equations, it would be cancelling each other. This, this is cancelled. This plus this, then this and this. You can see your overall equation. So this is the way how the homogeneous catalyst works. If you are not adding the catalyst into this system, so the reaction wouldn't be possible because they like the reactants would be repelling each other. So the reactants would be repelling each other. Okay, in this way the catalyst works. In this way the catalyst works. Like I'm talking about the homogeneous catalyst basically. Okay. Then I have heterogeneous catalyst. Then I have heterogeneous catalyst, how it works. So let's suppose heterogeneous catalyst means, let me give you an example. This is N2,3H2 and 2NH3. In this, we use the catalyst iron. Iron is solid and N2 is gas. This is also gas. Reactants are gases and the catalyst is solid. So this is heterogeneous catalyst. Okay, this is heterogeneous catalyst. And also this is C2H4, that is ethene, is going to react with H2 and it's going to form ethane, that is C2H6. So we used a catalyst that was nickel. I'm talking about organic chemistry. It is formed ethane. Okay. So you can see that this is the surface of nickel. This is the surface of nickel. Okay. Nickel has an ability, nickel has an ability to absorb hydrogen gas. Nickel has an ability to absorb hydrogen gas. Okay. To absorb hydrogen gas. So, you know, it has a lot of hydrogen gases H, 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 H. When ethene comes to this metal, when ethene comes to this metal, so it's going to make a bond, like attachment, just like that. It's going to absorb hydrogen from this metal, and you will see that it has desorbed hydrogen gas from that metal and ethane is formed. In this way, the heterogeneous catalyst works. In this way, the heterogeneous catalyst works. It's very simple. It's very simple. Okay. In this way, the heterogeneous catalyst works. So you must know about the homogeneous catalyst and you must know about like the heterogeneous catalyst. Okay. So first of all, you can see that it's going to make a new bond with that absorbed hydrogen gas into this metal, and then the double bond is going to break down, and you can see this ethane is formed. And you can see this ethane is formed. It's very simple. Okay. And then we have and then we have catalytic converter. Do you know about catalytic converter? Hmm? Basically, catalytic converter is going to convert harmful gases into harmless gases. Let's suppose the catalytic converter has platinum or palladium matte. It's a simple silencer which is used in different vehicles. So we simply fit platinum and palladium catalyst into this. Okay. And you will see that, let's suppose, let me draw the diagram of that catalytic converter. So it's very simple. Catalytic converter. Catalytic converter. So catalytic converter means that let's suppose you have this. I'm drawing a random diagram. This is entrance of carbon monoxide and nitrogen monoxide and unburned hydrocarbons. Okay. In this, platinum and palladium metal is fitted. Platinum and palladium metal is fitted. Okay. And this is exit of gases. You will see that carbon monoxide converted into CO2. NO is converted into NO2 and sorry, N2, and unburnt hydrocarbons would be converting into H2O. It's very simple. It's very simple. So the catalytic converter is going to decrease carbon monoxide and nitrogen monoxide emissions from internal combustion engines. From internal combustion engines. It's very simple. Okay. Let me tell you the type of reaction that the catalytic converter would give you. So number one, carbon monoxide would react with nitrogen monoxide. It would give you carbon dioxide and nitrogen gas. And nitrogen gas. Okay, it's a balanced reaction. You know, you know, monoxide is oxidized into dioxide, and NO is reduced to N2. NO is reduced to N2, and then hydrocarbons are going to react with nitrogen monoxide, and they are going to form CO2, H2O, and N2. Okay, so basically hydrogen and carbons are oxidized. Okay, they are oxidized. Okay, and and CO is going to react with oxygen. It's going to form CO2, or unburnt hydrocarbons are going to react with oxygen and it's going to form carbon dioxide and water. So I can say that in a catalytic converter, different reactions are going to take place. Some reactions are reduction reactions and some reactions are oxidation reactions. Some reactions are oxidation reactions and some reactions are reduction reactions. So specifically, generally speaking, that these two reactions are oxidation reactions. Okay. So we have to discuss this catalytic converter under under this heading, the catalyst. So can you justify that in this catalytic converter the platinum and palladium catalysts are platinum fitted with oh my god, fitted with platinum and palladium catalyst. Okay, so this is heterogeneous catalyst. This is heterogeneous catalyst. You know why? Because platinum and palladium, they both are solids, they both are metals, and these are gases. So of course they have a different state. Of course they have a different state. So that's why I am saying that this is heterogeneous catalyst. That's why I'm saying this is heterogeneous catalyst. Okay. And moreover, you know, your catalyst, that is platinum and palladium in that case, it would absorb carbon monoxide and nitrogen oxide molecules on the surface of that catalyst. Okay, on the surface of that catalyst. And of course, it's going to take some oxygens from that. And then it's going to form carbon dioxide and N2 molecules from the surface of the catalyst. From the surface of the catalyst. Okay, let me write it down so that you can write in your exam. Okay, number one, step number one. Step number one says that CO and NO molecules absorb onto the surface of the catalyst, okay, resulting in weakening of bonds and give chemical reaction. There are two main processes that are going to take place in the catalytic converter. First of all, it absorption and then desorption and then desorption. So number two step says desorption of carbon dioxide and N2 molecules, okay, from the surface of catalyst, from the surface of catalyst, okay. And then and then uh, you can say that we have autocatalyst. We have autocatalyst. You know what is autocatalyst? We have autocatalyst. We have autocatalyst. Okay. So autocatalyst means that let's suppose I have A, it's going to react with B, C and D is formed, and fortunately, fortunately, once the D is formed, once the D is formed, so the nature of the D is a catalyst. Fortunately, once the D is formed, so the nature of this is to act as a catalyst. It's very interesting. It's very interesting fact. So you will see that I can define it as one of the one of the one of the product formed one of the product formed in the reaction act as a catalyst act as a catalyst to speed up the reaction act as a catalyst to speed up the reaction to speed up the reaction. Okay, so specifically I can say when the manganate ions are going to react with H plus. Okay, like H plus is used as a catalyst, of course, and this is C2O42 minus oxalate ion. So MnO4 minus is reduced into Mn2 plus, and oxalate ion is oxidized into carbon dioxide and water is formed. Let me write the balanced chemical reaction. So it's 2 and it's 5 and then it's 2, then it's 10, then it's 8, and then we have 16 H positive ions. This reaction is very slow at room temperature. Very slow. Very slow. You know why? Because both are going to have a negative charge, of course. So there is repulsion. And of course, to start this reaction, activation energy is very high. Okay. Once the Mn2 plus is formed, so the Mn2 plus would be acting as a catalyst. And automatically, the speed would be increasing. Once Mn2 plus is formed, automatically the speed of the reaction would be increasing. In this way, autocatalyst is going to work. Same goes with hemoglobin. It's an iron 2 complex, of course. What is hemoglobin? It's an iron 2 complex and it's a polydentate ligand, and oxygen binds reversibly with an iron 2 plus. Of course, this is a ligand exchange reaction. So hemoglobin is replaced by a carbon monoxide with stronger dative bonds. So generally we say that what's the effect of carbon monoxide on the health of human body? So we can say carbon monoxide is going to react with hemoglobin and it's going to form a complex, carboxyhemoglobin. That complex is responsible to to stop the blood circulation, and result, the person would die. Okay, so that's all for the transition metals. Okay.